So today, we're going to totally move into a new bond type. Now, we've kind of talked about some of it. We've covered some of it. Today, we're going to talk about totally wrong. We're talking about covalent bonds. Above this slide, do me a favor, in big capital bold letters, write the word shared. S-H-A-R-E. Not share the single. Like, Mackenzie's going to share her Oreos with all of us.
Cheers. That's not even enough. Everybody gets one?
Kidding. Above this slide, write the word share. So the important part about the difference between ionic bonding and covalent bonding, in an ionic bond, what do electrons do? No. They're completely given up and completely taken. In a covalent bond, they are what? Shared. Now, just like Mackenzie, who's going to be stingy and not share her Oreos with everybody. Okay? There's two kinds of sharing. There's equal sharing, and there's also what? Unequal sharing.
Wait, what did you say to put on the
Share above. Okay? So a molecule. Let me go back to this. We talked about this the other day. As soon as you see that word, what word instantly has to come to mind? Covalent. Just like peanut butter and jelly. Molecule and... Try this again. Peanut butter and... Molecule and... Covalent, people. Covalent. Okay? Please connect those two dots. All right. So a molecule is a neutral. So let's stop there. Let's talk about this. What does neutral mean? It's not positive or negative. It's neutral. It's balanced. It's a neutral group of atoms that are held together by covalent bonds. Covalent bonding is a resulting of sharing of electron pairs. Now let's come in here and let's add this. I've already asked the question. You've already answered it. There's two types of sharing. What are they? Equal and unequal. Okay. Now, that's the real life word. We're going to add some science words to them. They're just as easy, but you've got to be able to connect the two. In a purely covalent bond, guys, y'all got to stop the chit chat. Like it's driving me crazy. Please stop. In a purely covalent bond, the shared electrons are on how? All right. So I'm going to kind of divert for just a second, and I want to kind of talk about those two concepts. So what is going to determine, let me change the color so you can see it. And I don't know how you want to write this, so once I finish it, you can kind of dictate how you want it to look. What determines equal versus unequal? We answered this on the second slide of this entire packet. Does anyone remember what property determines if electrons are shared equally or unequally? It's a long word that has like 15 syllables. Electronegativity. So, in order for us to determine if I'm going to share equally or if I'm going to be stingy and hold on to them, you have to know the electronegativity. We've talked about this. Remember bullies versus nerds. Who is the biggest bully? Fluorine. Fluorine. Does anyone remember its value?
-4.
Not negative. 4.0. Okay. Who's the biggest nerd? Francium. Top right, bottom left. Now the number really doesn't matter, but it's just out of curiosity. Anybody remember? 0.7. Very good. So what we've got to do is we've got to figure out where that balance is. We're going to look at that at the end of today. But what I want to do is talk about this. Now, go ahead and draw this. That's very simple, right? That's not complicated at all. Doesn't matter where. Doesn't matter where. You can do it at the bottom, top, left, doesn't matter. The first thing we have to discuss is what is that line between them? Starts with a B. A bond. You have to know this. If that line is a bond, so one line equals a bond. This next part is the most important part. How many electrons are in a bond? 2. Now, So when I write this in the future, I'm going to remove the middle word. Or I can remove the first word. I just need you to know that that line, which is a bond, is how many electrons? 2. Now this should also make sense. This line belongs to the left H and to the right H. So how many electrons does each H have?
1.
Try again. 2. It belongs to each. Because they're sharing, right? If we're sharing, we own both of them. Who is number 2? Look up there. What group is helium in? Is that a good thing? Yes. Remember, that's who everybody's trying to look like. So because we've now bonded H and H, is it who it wants to be? All right, so let's talk about this. Because this is a hydrogen and a hydrogen, now this is the trickiest one we do. Is hydrogen a metal or a non-metal? Very good. Now, why is that tricky? Because if I ask you this question, what side of that big orange line is it on? On the left. What do we normally say about elements on the left side? They're metals. But let's look back over here. Look in the top left corner. What color is the letter H?
Red.
Red. What state of matter is that?
Gas.
Gas. At what temperature? Can a gas be a metal? That doesn't make any sense at all, right? So we have to qualify hydrogen as what kind of element? Non-metal, right? So now let's ask that question again. Are those 2 metals or 2 non-metals? Now you should know the answer to this question. Since it's 2 non-metals, is that ionic or covalent? Covalent. 2 non-metals are covalent. By the end of today, that will be scorched into your brain. Okay, we're going to know that by the end of today. One more time. 2 non-metals is what type? Covalent. The slide we were just on, what big word did you write above that slide? So are they sharing those electrons? What we've got to figure out is how are they sharing them, equally or unequally? And I'll just ask the question, how do we know? What is it dependent upon? Electronegativity. So let me ask you this. Which H, this is a trick question, which H is more electronegative than the other? They're the same. So how do you think these electrons are going to be shared? Bingo. Let me show you how I draw this. So if this is an electron and they're being shared equally, do you agree that it's going to spend time around that H? Do you agree that it's going to spend time around that H? But because they're the same, will it be shared equal amounts of times? So do you agree that this is kind of what we would get? Try to trace that. Try to redraw that on your paper. All you're basically doing is drawing a figure 8 around both of them. The key is do the lines have to be equal on each side? Yes. The last component I'm going to add to this, I'm going to label something. This is not one of those things that's like critical right now at this moment you've got to grasp, but as we slowly begin to go through this, it will become more clear. So I'm dropping a nugget. This is all this is. This blue line represents this. Again, that's kind of a nugget that we'll get back to. But I'm just going to ask, what does it mean by electron density? Like how much is there, right? Are the electron densities on each side different or the same? Keep that in mind. Let's go to another drawing. First question, most important question. Are those metals or non-metals? How do you know? They're on the right side of the stair-step line. Since they're 2 non-metals, ionic or covalent? Covalent. What's happening with the electrons? They're being shared. In this case, the way we determine if it's equal or unequal is which property? That big long word. Electronegativity. Trick question. Which one's more electronegative? They're the same. So can I pretty much do the exact same thing here? Everybody okay with this? Same exact concept, right? Everybody okay with this so far? Let's go to the next one. This is where it changes. I'm going to ask the exact same set of questions. Are those metals or non-metals? Why is one of them a little weird? Hydrogen's on the left, but how do we treat it? As a non-metal. Covalent or ionic? Two nonmetals are covalent. Okay? Shared or given up. Shared. Now this time, something's a little different. Is there a difference in their electronegativity values? Yes. Which one's more electronegative? Absolutely F, right? Why? It's the most electronegative. So write these two things down and give yourself some space. And I want you to, there's a reason why. Write most E neg. Don't write it right up against the F, and you'll see why in just a second. Give yourself some space around the F. So now, if these two atoms are sharing this electron, do you agree that that's the initial phase? But what begins to happen because fluorine's more electronegative? It's going to take that electron and do what with it? Hold it. So it's going to do this. So now, what was that little nugget I dropped a minute ago? What does the blue line represent? Densities. Is it now the same? So is this equal or unequal? All right. So this is the English word. I'm going to ask a silly question. You know the answer. Why specifically is it unequal? Because fluorine is what? More electronegative. Let's now add the science word. Actually, let's not. Let me go one more step. So, we've now created an issue. Does one of those atoms have the electron around it more often than the other? Yes. So, if I am holding something negative, am I more negative or am I more positive? So, this is going to be negative. Write the negative sign down. Well, if one side is negative, then automatically, what does the other side have to turn? It's got to turn. Is everybody okay with that idea? Now, I'm going to come back to that in just a minute. So I'm going to add something, but we'll be there in a second. Now, let's go to the science word. What have I just created? A positive end and a negative end. So instead of saying unequal, what kind of covalent bond is this? Polar. And it should make sense. Since we have a positive pole and a negative pole, then what kind of bond is this? Polar. Do you see why we call it polar? Well, let's go back 2 slides. Are there poles on this one? So what do we call this type? Nonpolar. So it should make sense. Why are we calling it nonpolar? There are no poles. It's equal, right? Well, let's go back one more slide. What is that one? Nonpolar. Why is it nonpolar? There's no poles. It's not positive or negative. So do you see kind of the walkthrough of that? Does that help clear everything up? All right. So now let me go back and let me make sure I haven't missed anything. Put a big star beside the last bullet. And I want to reread the second bullet again. In a purely covalent bond, the shared electrons are owned equally. So somewhere around this little bullet, when it says equally, what word do you need to use? Nonpolar. So somewhere around that bullet, write the word nonpolar. And then the last bullet is, that's what we kept saying, right? Nonmetals and nonmetals to the right of the stair-step line are what type of bond? Covalent. So, excuse me, I should have kept reading. Right side of the stair-step line plus who? Hydrogen. Okay, so we want to make sure that we caught that. Now, everything, okay, check. So the electron of one atom and the proton of the other atom are attracted. Why is that true? Perfect. They are opposites. What is the charge of the electron? Negative. What's the charge of a proton? Positive. And what do opposites do? They attract. The two nuclei and the two electrons do what? Why are they repelling? They're the same. Help me out with the color scheme over there in the right drawing. Which color arrows are the attraction arrows? The red. They're pulling towards each other. Do you see how one is out there in that blue orbital and the other end is the positive nucleus, right? Negative and positive are coming together. What color arrow is the repulsion arrows? Blue. Why? Because what does the negative and the negative do to each other? Push. What does the positive and the positive do? Push, right? Does that make sense? This is the important part, it's the last bullet. These two forces do what? Cancel out. They form a covalent bond at the length where? Highlight those last several words. That's a test question. What is the energy at that length? At the minimum. Remember the other day I was asking you ever get lost in a store when you were young? When do you have the least amount of nervous energy? When you're with your mom, right? Same concept. The closer you are, the less energy you have. Now, do any of y'all have a friend or know a friend that gets way too close and they talk to you? They're kind of in your bubble. So we all know or have heard of that person. Guess what? Atoms are the same way. Is there a point where atoms can actually get too close to each other? Yes. So let's look at this. I'm telling you now, you might see a question on the test like this graph. So what I'm going to do is I'm going to kind of give you an idea of what it'll look like. 1, this is 2, this is 3, this is 4. Which set of atoms, okay, 1, 2, 3, or 4, just raise your hand with a number, has the lowest potential energy? Hold up your fingers. 1, 2, 3, or 4. Which one's the lowest potential energy? If you miss that question, we have a problem. It literally says it right beside it. 2. Now, there's a sweet spot of how close they can be to be at the lowest potential energy. So let's start with 1. What's wrong with 1? Why is the potential energy so high? Too close, right? That's that person that gets up in your grills and wants to talk to you like, no, I can smell your breath, you're going to eat Doritos, like back up, right? Okay? Or Oreos, whatever they're eating for lunch. Didn't even think. So then, as you notice, if they kind of start getting at a good distance, what happens to the potential energy from 1 to 2? It starts going down. And then it's at a perfect spot, and then it starts to come back up. So what's occurring from 2 to 3? They're getting kind of too far apart, right? They're struggling to hold on to each other, right? So it's like they're just enough where there's some attraction, but it's a little too far away. And then what happens at step 4? They're too far apart. So what is no longer occurring between them at all? There's no forces of attraction. So here's what I always ask students. Why does the graph not do this? Why does it come up and level off at a value of 0? They're too far apart. There's no potential energy from them, right? Can I have any energy with someone in another room? No, not at all, right? So that's kind of the concept. We're too far apart, so there's nothing between us. So that's what's going on. So one more time, exact same sentence as the previous slide. Most atoms have lower potential energy when they're bonded compared to independent particles. So again, but is there a sweet spot? Yes. Is there something that's being too close? Yes. Okay, so make sure you understand the components of that graph. All right. Now, we'll go ahead and take it. The top bullet and the bottom bullet are test questions. The top bullet and the bottom bullet are test questions. The top bullet is very simple. Like it is a verbatim regurgitation of a definition. Like if you called Webster, this is what Webster would tell you. The distance between bonded atoms when at their minimum potential energy is called the what? Bond length. What do you think a possible wrong answer you may see on the test is? Very good. Don't get them backwards. The bond length is when the potential energy is at its what? Minimum. I'm telling you now, somebody's going to miss that question because they're going to pick maximum. It's the minimum. Okay? So what does that matter? Forming a covalent bond, the hydrogen atoms release energy. This is a good point. What type of reaction was when we released energy? Everybody remember? Very first unit. Say that again? Very good. It's exothermic. Does anyone remember the sign of delta H? Oh, that was positive or negative?
Triangle.
Negative. negative delta H. Because exothermic releases energy. Last question, hot or cold? Try again. Okay? Most exothermic reactions, when they release energy, they warm up their surroundings. Okay? So that's what's going on there. Now, the same amount of energy must be added to separate the bonds. So, since you just blew your nose, I'm not going to do this. Say it here. Okay. So, high five me. Do it again. Did we just release some energy?
Yeah.
It's sound a form of energy.
Yes.
One more time. All right. Now, let's do it again, but stick it. 1, 2, 3. So, if you wanted to pull us apart, how much energy would you have to put in to pull us back apart? The same amount that we released. Does that make sense? Thank you. So if you put two things together, they release energy. Well, once they're stuck, how do you then get them back apart? It's the same amount of energy that has to go back in. Does that make sense? So this is what ties into the last bullet. Highlight the first blue word. So we've talked about bond length, which is the distance. Is length the distance? Yes. It's the distance between atoms at the minimum energy. Bond energy is the energy required to do what? Break. What do you think a possible wrong answer you may see is? To make a bond. Don't choose the wrong one. Bond length is the minimum energy. Bond energy is the energy required to break a bond. And the way I like to think about it is a karate board. If you have to break a board, what do you have to do with energy? Put it in. Does that board have board energy? Yes. Same concept. Okay? All right. Now, y'all have this? I don't remember if I left this in or not. Okay, so let's just look up here. Here's the first thing I want to do. I want to compare everything in that black box. What do all of the atoms in that black box have in common? They're all hydrogens. What do they all have in, how are they dissimilar? Their second element's all different. Now, here's the other question. So what we're talking about here are bond energies. All right, bond energies. So what is again the bond energy? Make or break it? Break. Energy required to break. In that black box, which compound requires the most energy to break it? Which two? HF. Someone tell me, why do you think H and F would require the most amount of energy? Fluorine is the most electronegative. So what does it want to do with its electrons? Hold on to them. They don't want to get rid of them, right? So that's what's going on. Let's look at another set. Now these are all going to be kind of random across the board. Actually, let's do this one. So in the orange box, what do all of those atoms have in common? They're all carbon and everything else is different, right? Which bond set requires the most amount of energy to break? Does that follow the same trend we've been talking about? Now, here's where it gets a little different. Let's look at, again, this is going to be hard to do, but let's look at this one, and then let's look at those two. What do those have in common? They're all nitrogens. But what's different about them? Okay, so the one on the far left by itself is a single bond. The top one over here is a double, and the bottom one's a triple. Which one, single, double, or triple, requires the most amount of energy to break? The triple. If I took you to karate class and said, here's one board, here's two boards, here's three boards, which one's going to be the hardest one to break? The triple. Does that make logical sense? We cool with that? All right, here's the last topic. Let's look at the first three. Right here. Actually, let's do this. Let me go all the way across. What do those all have in common? They're all carbon, carbon, carbon. How are they different? So one's single, one's double, one's triple. Look in the far right column. Which one would you expect to require the most amount of energy to break? The triple. Is that true? Yes. Now, go back to the middle column. Someone relate bond energy and bond type to the bond length? Say it. The more bonds you have, the shorter the length gets. Let me show you an example. Is this a stick? Okay, does it have a specific length? If I were to take this, would it require a whole lot of energy to break this stick in half? No. Well, let's say I break it in half and I take this half and just throw it away. So now I've just got this half, right? Is it got a little bit harder or a little bit easier? A little bit harder, right? So let's say I break it in half and I get down to this and I throw it in. So this is all I have. Does it get harder or easier? So the shorter it gets, the harder it gets. Does that make sense? Okay. The other way I say it, if I break this in half, how many equal pieces do I have? Two equal pieces. Now, if I've got this end and this, and so I've got two of them, then it get even harder to break. Now it's two of them that I got to break, and it's even shorter. Well, what happens if I could break those in half, and then I put three of them together? Is that even harder to break? So do you see what's happening? Not only is it getting shorter, but you're also adding more of them. So does that make sense why it increases? All right. So hopefully that clicks, and that makes sense. All right. So everything we've already talked about is exactly what we've already covered when I drew on the board earlier. So put a big circle or highlight around those two words. When you see the word non-polar, how are the electrons being shared? Equally. And if you want to, this may be a situation where you can do this. I'm going to pick two other elements. I'm going to pick iodine and iodine. First of all, is that a diatomic? How do you know? Two of the same ones. Is it one of the 7 diatomics? Does it end in gin? Or does it? Is it a halogen? Oh yeah, right? Is it a part of the gun and the bullet? Yes, it's a part of the gun and the bullet. So this is the iodine. Now, which one of those two, and this is a trick question, which one of the two is more electronegative? They're the same. So how are they going to share their electrons? Equally. So, when you're finished, what are the electron densities? The same. So that is a polar or non-polar deal. This is non-polar. So look at the last sentence. Have I been talking about that already? You've already seen it, right? The electron densities should be equal. So I think this is a picture. Now, let's ignore the top, but let's look at the bottom. Those color spectrums is any one side more of a color than the other? The bottom one. They're the same colors, right? So is there any difference in sharing of electrons there? No, so those are non-polar. Now the top is where it gets a little strange. Is there a difference in electron densities up here? There are. How can you tell? The colors. So this compound is actually carbon dioxide. So in here is carbon. Try this again with a different pen. This is carbon and this is oxygen. So let's just focus on one side of this. Which one's more electronegative, carbon or oxygen? Who's closer to fluorine? Oxygen. So is oxygen going to pull the electrons closer to it? So what's going to happen here, and I want you to draw this on here. So this is going to look like this. Okay? Not only is that occurring on the left one, where else is it occurring? On the right one as well. Does everyone agree with that? So watch what happens. So you've got this going on. So here's the deal. Do you agree that the carbon is having its electrons pulled out in both directions? But here's the deal. Here's the problem. Which oxygen is pulling more strongly? Neither. So if I took Trinity and put her in the center, and I wrapped the rope around her, and then I cloned myself and put the other guy on the other side with another rope, and we started pulling in opposite directions, who's going to win? Neither one. So what's going to happen to the polarness of this molecule? They're going to cancel each other out. So even though that top molecule looks polar, what has happened to it? It's been canceled, so it's still what? Non-polar. Does that make sense at all? Yes, no, maybe. All right. So, the other silly pictures. Two penguins have an arm wrestling match. Which penguin's going to win? Neither one of them. Two polar bears get an arm wrestling match. Which polar bear is going to win? Neither one.
The one who's relaxed.
He does kind of look confident, doesn't he? So, but what happens if a polar bear and a penguin get in a match? Definitely a polar bear, right? So that is when we start talking about other things. Okay? All right. Now, again, same concept. But this time, we're talking about polar molecules and how are they being shared? Unequal. Again, this is everything I've already talked about. We put this in drawings. Now we're putting it in words. This next little sentence is probably the most important to understand the why. You've seen the what. Now let's talk about the why. Why are molecules polar? Let's read the second sentence. The more electronegative atom. Now, who's the most electronegative? Fluorine. How can you compare two atoms if you don't know their numbers? Who's closest to fluorine? That's how you'll know, right? So the more electronegative atom pulls stronger on the valence electrons. I'm going to stop there. I'm going to go back to the last unit. Which orbitals are valence? Very good. S and P. Just throw that in there. Pulling them closer to itself, that creates an uneven distribution of charge. Now, remember a second ago I told you I was going to go back to one of the drawings. Here's the problem. We've been saying this now for the past 30 minutes. In a covalent bond, how are electrons shared? How are electrons treated? They're being shared. So in this case, are they equally shared or unequally shared? Unequally. Here's the question I have to ask. You've told me they're being shared. So is that different than me literally giving them to you? Yes. So here's the question. Is this fluorine fully negative? It's only kind of negative. Read the last bullet on your slide. What does it say? The other end of the bond has a what kind of charge? A partial negative charge. And the other end has an equal partial positive charge. Now, when we come over here, do you want to write the word partial by all that? No. There's a little symbol. Look on your PowerPoint slide. That little symbol is kind of weird looking, right? So here's what it is. This is how I draw it. It's like an S where its tail touches, or it's an 8, you got lazy and didn't finish. I don't care which one you use. But go back to this drawing and add those two things. So when you see them, what word has to come to mind? Partial. It's partially positive, partially negative. Now, because it looks like an S, I actually used to use another word, and I didn't even know it, but I asked their block yesterday because they're a little ahead of you guys. Can you give me another word that's a synonym to partial that begins with an S? And they threw out two of them I never even thought of.
Synonym.
What is a synonym, first of all? So, yeah, that begins with an S.
Section.
They threw out two. Semi, right? The other one they threw out was sorta.
Sort of.
Here's the one I always use, and they were like, that's dumb. And I was like, I don't care.
Slightly.
Slightly.
Hey, that's it.
So,
Sort of slight.
does it matter which one you use? No. The reason I say why an S is because, again, what does this little symbol look like? Kind of looks like an S. Now, some of you may care, some of you may not care, but I'm still going to tell you this anyway. Does the English alphabet, Gabriel, have a capital letter and a lowercase letter?
Yes.
This is a Greek symbol. Do Greek symbols also have capital letters and lowercase letters? They do. Actually, and again, that's a fact that some of you could care less about, but I'm telling you truth through students. So, just a second. This is a lowercase Greek letter. You know already the capital Greek letter for this. This is delta. What is capital delta? A triangle. What is lowercase delta? That thing. So, if you care at all, it doesn't matter, but you have a little bit of knowledge now that that is a lowercase delta. Yeah, you can go. Okay. So, again, if I ask you to write capital delta, it's a triangle. If I ask you to write a lowercase delta, it's this funky looking S thing. And what does it mean in English words? Partial, semi, sorta, slightly. But they all mean the same thing, right? What I'm trying to get at is this. Is it fully negative and fully positive? No, it's slightly positive and slightly negative. All right, so let's go to the next one. Two more slides and we're done. This is the part that kind of gets a little strange, but it makes sense. In science, you can dissect words and it makes a whole lot more sense. Remember when we dissected intermolecular forces and it made more sense? We can do that with dipole. So where am I going to dissect this word? Dipole. Very good. So let's split it right down there. What does the prefix di mean? It means two. What does the word pole mean? It's pole, right? Now, that's okay, but we need to get a little more specific than pole. What are the two pole types? Positive and negative. So there's two poles. There's a positive pole and there's a negative pole, which is called a dipole. Has two poles. The poles are positive, the poles are negative. That second bullet is the most important. The second bullet is the most important. Because you've got to be able to decide how to draw the dipole, because it has a direction. Now, I asked this question earlier, and I'm actually just fishing. I don't know if I'm going to catch anything, because I'm just pure curious if you can do it, because I struggle with this. Define the word direction.
What?
You see what I'm saying? It's kind of hard to define direction. You know what it is. It's very intuitive of a direction, but it's still hard to define. So while I'm going fishing, I didn't know what I was going to catch there.
Oh, that's just weird.
It is weird, right? It's one of those words you know exactly what it means, but you don't know how to define it.
A course along which something, someone, or someone moves.
A course that moves.
A course along which someone or something moves.
A course along something moves. Okay. So let's keep reading. The direction of a dipole, highlight those blue words, is from the positive to the negative. Does the direction have a point to? Yes. So it's going to be pointing towards which end? It's from the positive pointing to the negative. Okay? So pointing from positive to negative. Now, this third bullet gives a little bit more clarity. Each polar bond has a dipole. This is where it gets a little muddy, so stay with me. However, the overall dipole for the molecule is different, potentially, than the dipoles themselves. So the only way to explain it is to draw it. So let me draw it up here for you. I'm actually going to redraw that bottom left picture. So let me start out with simple questions, just like I did a few minutes ago. Carbon and oxygen, metals or non-metals? Non-metals. Covalent or ionic? Covalent. Now, this is an important question. I'm shifting gears now. Between each O and each C, there's two little lines. What do those things represent? What kind of bonds? These are double bonds. So in this case, we've got double bonds. Now, I'm going to ask this question, and it should make sense as we walk ourselves through it. So, each double bond, and there's two of them, right? Do you agree? There's one on the left, one on the right. How many electrons are in the left double bond? This goes back to the very beginning. What does one line represent? Two. So if there's two lines, there are four. So the left one has four. Do you agree? Well, if the left one has four, how many does the right one have? So how many total electrons are on those 4 lines? 8. What does every element try to have? Does carbon have its 8 electrons? Yes. Now, I know what you're going to say. Well, what about oxygen? We'll get to that. Hold that thought for a later date. We're going to get there. I'm going to explain that later. That's the first part of this. The second part is we've got to figure out how these electrons are being shared. Are they equal sharing or unequal sharing? We've already done this, but let's do it again. Let's just look at these two. Is one of those two more electronegative than the other? Which one? How do you know it's oxygen? It's closer to fluorine. So if I draw this, which one is it going to spend more time around? So does this occur? Everybody okay with that? Now let's look at the other side. Is this occurring? But who's it going to spend more time around? Does that make sense? So my question to you is this. Is this thing polar on each end? Yes. So do you agree that this end is partially negative, this end is partially negative, and the middle is partially positive? Someone tell me why the ends are negatives and not positives.
Because they're,
The electrons are on the ends. Does everyone agree with that? Now, someone go back and reread the second bullet. Lillian, do me a favor, read it out loud. Read the second bullet on that slide we were just on. Yep.
The direction of a dipole is from the dipole's positive pole to its negative pole.
All right, so let's look at the left side, the left one. What direction is the arrow going to point? Is the arrow going to point to the left, or is the arrow going to point to the right? It's pointing from positive to negative. Very good. So it's going to point this way, and it's going to point that way. So here's my question. There's 2 dipoles in this thing, correct?
No.
But what happens to the overall molecule? Which oxygen's going to win? Neither one of them. So reread that third bullet, Lillian.
Each polar bond has a dipole.
Pulse. Each polar bond has that's both arrows. Keep reading.
Which leads to an overall dipole.
Pulse. Both of those arrows are working against each other. Right? So keep reading.
Which actually determines if the molecular is a polar or non-polar.
So if those 2 arrows are going in opposite directions, what's going to happen to them? They're going to cancel. So what's the entire molecule then? Non-polar. Okay? The entire thing is non-polar. Does that make any sense at all? If it doesn't today, we're going to continue working on this, and I promise you it will make more sense. So I'm going to ignore the bottom right one. I'll come back to that at a later date when I feel like it's going to make a little bit more sense to you guys. And let me show you one last slide, and then I'm going to do something else. All right. Actually, 2 last slides. Let's look at this thing. Are the electron densities majorly different in that compound? How can you tell based on the colors? One's red, one's blue. How can you tell based on the atoms? Fluorine is more. So which end is negative? The hydrogen end or the fluorine end? So this end, do this for me. Do y'all have this slide? So this end's partially negative, and this end is partially positive. And I'm asking this just to make sure everybody's on the same page. Why is it only partially positive and partially negative and not fully positive and negative? The electrons are being shared. All right. So that is a dipole. Okay. Let's look down here at the water. Is this a polar molecule?
No.
Yes. Why? Because the electrons are going in opposite directions. Okay. Which end's negative? So this is partially negative, that's partially positive, and that's partially positive. Okay? Alright. Let me show you 4 more, and we're done. Let's look at the top. Y'all don't have this one, so you have to look up here. Wait 1 second. HCl, top left. Polar or non-polar? How can you tell? It's uneven, right? It's more electronegative on one end than the other. Which end's the negative end, the left end or the right end? Right end. Everybody okay with that? The top right one, H2S. Polar or non-polar? Polar. Because there's more electrons down at the bottom end than there are at the top, right? So is the negative on the bottom or the top? Bottom. Be very careful on this next one. Look at the bottom left one. SO3. Polar or non-polar? This one's non-polar. Here's why. Are there polar parts to it? Yes. But what happens to this S? That's pulling that way, that's pulling that way, and that's pulling up. What's happening to the S? They can't. Do they cancel each other out? Yes. Does that make sense? Last one. The one on the bottom right is this that I have in my hand. So, when that black sphere starts pulling on all those red spheres in towards itself, because all the red ones are the same, which red sphere is going to get closer to the black? None of them. So what does that mean about the polarity of this thing? It's non-polar. Okay? Does that make sense? Now, let me throw a kink into this thing. And it will make sense. What if someone comes along and changes one of these oxygens to a fluorine? Is now one of them stronger than the other? Yes. So would it stay non-polar? It would change. What if someone comes along to this and changes that to a fluorine? Is it still non-polar? No. So do you see how the atoms also matter in all this? Yes, sir. Just a minute. So here's what I want to do. I told you by the end of the day that you guys are going to know ionic versus covalent. And that's what this is. For today. No, it's not over.
That was a good one. That was a good one. I said, I already I'm so stupid. Today's a sleepy day. Training. It's a sleepy day.
So you are going to need the periodic table underneath your desk. You'll go ahead and get it out.
Also have my glove.
Up on the front counter.
Give me that one.
Yeah, he's a darling. He's weird. He's definitely there. Mr. Moro is a Friday.
All right. So let's start. This is the front side. This right here. This is the front. So let's start on this end. Start on this side. This is the front. So let's look at the very top. It says ionic bond is between a what? A cation. And what are cations? No. Yes, that's true. But they're also what type of elements? Metals. What side of the stair step line are they on?
Left.
Write the word left above those two words.
Which one?
Wait, what?
Sorry.
An ionic bond, where it says between a cation, parenthesis, metal, right left above those two words. And an anion, which is what charge? Negative. And what type of element? Non-metal. Where is that on the stair step line? The right side. Now, the other thing is right below it, big bold star. Don't forget about your polyatomic ions. We're going to see one of those and we'll show you in just a second. Okay? Now, a covalent bond is between what two types? Non-metal and a non-metal. And what are those on? Each one. The right. Now, I'm going to go ahead and throw you a curveball. What is the other element that's a non-metal but not on the right side? So you may want to write and hydrogen beside that. So between a non-metal and a non-metal and hydrogen. You may want to jot that down because that's going to come into play in this. All right, the last one. A metallic bond is between a what and a what? Metal and a metal. And they're both going to be on which side of the stair step? Left side. Everybody with me? So let's do the first few together out loud so you can see how this works. The first one's already done for you, so let's talk through it. The first element is N. What is it? What type of element?
Nitrogen.
It is nitrogen, but what type of element? How do you know?
It's on the left.
It's on the right side. All right. The second element listed is O. Is it a metal or a non-metal?
Non-metal.
We'll do the first row. How do you know it's a non-metal?
Because it's
It's on the right. So when you have a non-metal and a non-metal, what type of bond is that? Covalent. Now here's the problem. We've been talking about polar and non-polar this whole time, right? Here's the issue. You cannot, NOT, you cannot determine whether it's polar or non-polar unless you draw it. We will draw them next week. And that's when you'll begin to determine that part of this. But for today, you will not be able to determine that on the front side. We'll talk about the back in a minute. All right, so let's go to the next one. All right, what's the first element listed? Write that in the first empty column. Write Na and write equals. Is that a metal or a non-metal? How do you know? It's on the left. All right. What's the second element? So write Cl equals in the second empty column. Is that a metal or a non-metal? How do you know it's a non-metal? It's on the right of the stair step. So we have a metal and a non-metal. So what type of bond is that? Ion. Everybody okay with this? We'll do one more for you. Go to the fourth one. So skip SO2 and go to the one right below. Right? What's the first element listed? Right, Na. Na equals metal or non-metal. How do you know? To the left. Now, Na. Go to the fourth one. Na, 3PO4. All right, this is where it gets weird. PO and 4. Phosphate. That's phosphate. So I'm going to explain something in just a second. So what is phosphate? It is a polyatomic ion. So in that second empty column, write PO4. And I'm going to get up on the board and show you in just a second. Does anyone remember the charge of phosphate? 3 negative. It's the only one that's 3 negative. So write PO4, 3 negative. Now, I know what you're going to say. Was that a metal or a non-metal? It's a polyatomic ion. So write P, or you can go to P if you want to put a P, but it's a polyatomic ion. So, if you have a metal and a polyatomic ion, thank you, ma'am. It's an ionic bond. Everybody with me? Now, here's what I want to clarify. And this will make perfect sense when you see it. This is the formula. Do you agree? Everybody okay with that? You guys told me that phosphate is PO4 3 minus. So the question you may have is, well, in this formula, where did the 3 minus go? Let me explain that. So every compound must be balanced. It must be neutral. So if phosphate is 3 negative, then how many positives do I have to have? Got to have 3. So let's say we're going to partner it with sodium. Does anyone happen to remember the charge of sodium? It's 1 plus. So if I've got 3 negatives and I've got 1 positive, I need to have how many more positives? I need 2 more. Now, is it balanced? Is this a good way to write this? No. So what can you do with all of these guys? Na3. Does that make sense? So that formula tells you there are how many sodiums? 3. Now, the other question is, well, why doesn't phosphate have anything? Let me show you that. So if I have this, here's what we can do with it. I can take these charges and I can crisscross them. I can drop this here and that there. Does this now look familiar? But the question is, well, why don't you deal with that? What number is that to be understood as? Do I really need to put a 1 back here? Sure don't. So does this all make sense? This is where we're going in the next unit. Is being able to pull this off. Okay? All right. So Everybody flip over to the back. Now, I'm going to go ahead and tell you, the beginning of this discussion is going to be a little weird, and I'm going to clear it up. So just forewarning, it's not going to make sense, but I'm going to clear it up. Now, I need to correct some things. You see in the top right-hand part of the periodic table, you can't see those numbers. So let me give you what those numbers are, so please write these down. Does everybody know where fluorine is on the periodic table? You can't see that box. In that box, anybody can remember the number? 4.0. So the fluorine value is 4.0. All right, go to the left one box. What element is that? What? Can everybody tell us?
3.5.
3.5. You can't see it, write it down above. 3.5. All right, go left one more. That's nitrogen. That's 3.0. That's where I'm headed next. So what is under fluorine?
Calcium.
Try again. Fluorine. What is its value in the box? Is 3.0. Okay, so one more time. Fluorine is 4.0. Going left one is 3.5. Going left one more is 3.0. Going back over to fluorine, going down one. That is 3.0 as well. So I just want to make sure everybody knows the numbers. Now, you are going to have to do one small, tiny subtraction. If you want to use your phone calculator, that's perfectly fine. It's going to be very easy. Most of you can probably do it in your head. So here's what I'll do. Let's look at the very bottom sets of boxes. So we got to compare sulfur and hydrogen. So everybody find sulfur, everybody find hydrogen. What is the value of hydrogen? 2.1. What is the value of sulfur? All right, so look back down there in the bottom box. The first empty column is the more electronegative element and value. So which element's going in that box? Sulfur. So write S equals, and what was its value again? 2.5. All right. The second empty column is the less electronegative element and value. So what would it be? Hydrogen equals 2.1. Now, the electronegativity difference, just subtract 0.4. This is where the wheels are going to fall off for just a second, but I'm going to clear it up. Now, do you see that there are two different boxes with electronegativity values and bond types? Everybody look at, someone tell me, and I don't care which box you use the top one or the bottom one, what is the bond type? Folded. Don't start yelling at each other about it. Sir, why? Yeah, but I see one that says polar.
Polar. What's different though?
They're different. Look at the one that goes left to right. What is the non-polar difference? 0 to 0.3. Go to the one below it. It's 0 to 0.49. So do you see the difference? So this is why we're not going to do the math on this, because are there different chart values? So for this exercise, do you see the one that has the big complicated box with all the words in it? Put an X through that one and use the one that goes left to right.
That's confusing me. No, I like little words.
No, so use the one that says 4.0, 1.7, 0.3, and 0. Just use that one. Don't use the other one.
So this whole thing?
Yeah, just put an X through that. The one, you see where it says percentages of atomic character? All that box below where it says percentage of atomic character, cross it off.
So just as either polar or...
So in that case, it is polar.
Told you.
So everybody's answer needs to be using that top one that goes left to right. And did I not say it's going to get weird? That's why. This is why we don't use the calculations, because it doesn't matter which set of numbers you use. Well, we're going to default back to is it a metal versus non-metal. One more question. When you do some of these, I'm going to forewarn you, the numbers are going to fall right on the line. What do? Do exactly what you did back on the front. Determine if it's a metal or a non-metal and decide from there. Okay, Caroline, this man. That's the answer. Do exactly what you have done back on the front. So I would recommend going back to the front, starting with it, and the back will go a whole lot faster. Go back to the front, do it, and the back will go faster. Exactly. Split
If it's
One in each box.
What about the third one? Like the last one?
Okay, so real quick, go back to the front. Go back to the front. The very bottom row. There are 3 elements, just make 3 columns at the bottom. Go back to the front. The bottom box, there are 3 the bottom row, there are 3 elements, just make 3 columns at the bottom. That'll solve that issue. All right. That's what I was saying. So go back to the front and figure out if it's a metal or non-metal and what it should be based on that. So you should, by the end of this sheet, be able to take any compound I give you and diagnose it and determine its bond type. This is what you have to be able to do at a minimum to be successful. Yeah, you can write, if you want to write NM for non-metal and M or NET for metal, that's fine. I don't care. As long as you know what it is, that's fine. Just follow along.
That's
Just
trash.
do what you did for all the others.
I looked up what trash.
Is that what it was? Thank you for looking that up.
So I figured you weren't gonna look it up.
I was. Yep, yep. And that kind of makes sense because it's a penny with the color.
Wait, okay,
Dude, I swear you're on like what? I don't feel like
That's a federal crime.
Yeah, because
It's like you can't write on money or tear
because the
tax.
materials that use
Federal crime.
the materials that it's used to create things are it's like 1.07 cents. So it's cost. So a penny is more important. It's worth more than that.
Make sure y'all.
A penny is worth more than 1 cent, even though it's 1 cent. That's why you can't let that. It's illegal. It's illegal. Whoa. I don't you're saying that shit about that patch.
Come on, come on, come on. Yep. Why? It's a metal in a metal. Yep, just follow the rules. That won't lead you wrong.
I turned in my version. It's still listed, right?
Say non-metal. Yep. That's what it said right here. Non-metal on the end.
It's 2 metallic bonds.
You just ask what it's called. Huh?
Trini has a better grade in this patch. She asked me for everything. It's so annoying. See, you know exactly what you're doing.
Have you seen my back question?
Right is non-metal. You have to for every game, you know every name. You'd be like, I'm gonna fail in that game. CO is green. That's I keep on mixing them up. Like, I know what I'm doing. I just keep on moving them. Trinity, do you know virus? It's a gas. It's about why does it say no metal present on it? Because it's nitrate?
So it's N is in the first column, O is in the second column. Because there's no metal present, that means it can't be an ion. Makes sense?
I don't understand. Why did it tell us?
Is that because every year someone messed that up? Because it's an ion, they want to make it ionic.
Oh,
Which doesn't turn into an ionic bond until it is with a metal. So let me prove that to you. Right here. Certain atoms bond covalently with each other to form a group of atoms that have both
titanium, I forgot titanium was an element, those are certain.
Split it, right one of those boxes. Split it.
Who's up there writing?
Actually, yeah.
Yes, sir.
Is there ever a place for writing in here? No,
No, it's never a metal, but yes, it is a cation. See where it says cations or metals? Hydrogen is never a metal, but it is a cation. So it's weird in this little section. So no, it's not ever a metal, but it acts like a cation. Split it one of these boxes.
Where's this?
Put it just out of their box. Yeah, because they're all non-metal, right? Alright, so again, this is why I said there's no difference. So N is the first one, O is the second one, and follow the rules. Yep. So, and the reason that's true is yes, it's an ion. However, it does not turn into an ionic bond until a metal shows up. There's no metal. Does that make sense?
You got a good pull.
Yes, split it one of these bonds. Yep. Put it on the same box, because there's two O's, right? Again, just a reminder, hydrogen, metal or non-metal? Non-metal, keep that in mind, don't forget that. Hydrogen's a non-metal. Yep, go ahead. Yep. Once you get the back, it's going to go a whole lot faster.
I forgot what I was just saying.
We just have to do a little bit more math, but the content gets easier.
No, I have to search a lot more.
It says.
Why have to be a break?
By the way, let me just say this out loud. When you flip over, get to the back, if you get a negative number, you've done something wrong. Very good. You caught an issue. It's right. Leave it alone. I'm going to address it. You caught the issue. Yep, you caught the issue. Follow what it says, and I'm going to address that. So when they follow the same, do exactly what you did on the front. Look back at the middle.
This has some
Okay,
difference.
so non-metal and then metal or non-metal.
Look here, it makes perfect sense. It makes perfect sense.
Put one in each box. And the reason why is because there's two of them.
I'm gonna look up alternative one.
The H goes on.
I don't know. Okay, when I put it on, this one 1.7. Wait, so when it's on the line, what you said there?
So when it's on the line, do exactly what you did back in the front. Find out, are they two, is it a metal and a non-metal, or is it two non-metals? Why can't you just take the staircase and just take it all the way across, just cut it, just make it easier? Never thought about it like that. I like that. So that's basically like you've reached the top floor, keep walking across. Huh.
It would still be across. It would be still there, yeah. They just went all the line.
Wait, what?
I'm going to show you. I'm going to draw it on the board.
I thought it was just so simple.
Hey, let me show you this real quick. I love when you guys create things that are out of the box that I just don't see, I don't think. But Antonio said this is a unique way. Gabriel, y'all listen for just a second. Okay, a unique way to remember hydrogen. So if you start down here and you're walking up the stairs, just pretend you've reached the floor and it comes all the way over. So hydrogen is technically on that side.
That's cool.
Again, that may not work for you, but That's unique. I've never seen that, heard that, or thought about that. So if you just pretend you've reached the top floor, hydrogen is on that floor, so it has to go to that side, right? It's the only way you can get down to this side, is it's across the floor. Again, if you don't like it, that's fine.